All right. Welcome to the first episode of Gears of Resistance, which is hopefully going to be a new podcast we're going to do on a bi-weekly or maybe once a month basis that covers open source hardware. And I'm still not sure exactly the format, whether we're going to do product reviews or if we're going to do projects reviews and get people in here to talk about their projects. We'll probably end up doing a little bit of everything, at least initially. But it's been, I'd say, of all the feedback I get through the blogs and the podcasts, it's the questions are always comes back to questions on how to do electronics projects, and specifically things like the Arduino, the Raspberry Pi, Beagle Bone, what else? Fidgets, and a few other kits keep coming up specifically. So we're going to try to fill that niche, so to speak. There's a couple podcasts out there, at least a few I found, that deal with the similar idea of open source hardware, but not quite the way I think I want to handle it. The one is do it more of a video based. There's a few out there, but also make it enjoyable enough that you could actually just listen as well. So I'll hopefully find a nice blend, nice balance between having a lot of video intensive, because at the end of the day, electronics is about showing the different parts, but also having a good conversation so that's enjoyable just to listen to. So with that, the first question that we're going to tackle in here in the first episode is the one I get the most, which is I'm getting started in electronics. What is the first platform I should develop for? And I will give you the engineering answer, the best engineering answer. And this is how you can tell if you have a good engineer or not, is if the answer, if they give you as well, it depends. There really is, it depends on the requirements, or what are you trying to accomplish. Every type of board has its pros and cons. And so we're also not going to talk about every particular model that's out there, because there are tons. Even just within the Arduino family, there's probably a dozen, if not more, different types of Arduinos. And so we're going to talk about today at a sort of a higher level, the difference between an Arduino, which is a microcontroller based solution, and Raspberry Pi, which is a single board computer solution. Now, it's kind of hard to, on the outset, think that there's a difference, but there is actually a big difference between Arduinos and Raspberry Pis. And again, depending on what you're trying to accomplish, you may need one or the other, or there's a lot of good solutions that have that incorporate both. And there's a third type of hardware platform that is getting open sourceified, I'd say, and that is Field Programmable Gate Arrays, which they're not quite as easy to wrap your head around, or are they as available or plentiful as things like Raspberry Pi, Beagle Bones, Arduinos yet. They're starting to get there, and we'll talk about that too. So the idea today is, again, there's three types. They're platforms that we're going to kind of discuss at a high level: microcontrollers, single board computers, and field programmable gate arrays. And what does each do? What are the pros and cons of each? And which, when you're kind of kicking off a project, what are you going to look for? So with that in mind, let's go ahead and let's start off. I'm going to switch over to a different camera here. And let's see if this works. Cool. I think that works. So let's first talk about a microcontroller, and specifically the Arduino. Now, Arduino is a platform. It isn't necessarily specifically the microcontroller. So there's two really big microcontroller families out there. The ATMEL, ATMEGA line, which the Arduino is based upon. And there's Microchip has their PIC line of microcontrollers, PIC. Texas Instruments has the MSP 430 line that's popular with hobbyists and semi-professional makers. But the one that's kind of got all the rage right now is Arduino. And again, it isn't a microcontroller. It uses an ATMEL ATMEGA microcontroller at the heart and adds additional features like power voltage regulation. It makes it easy. It gives you the header pins to be able to easily access the I/O on the chip. It provides the clock, an oscillator to provide the clock signal. So the Arduino is a platform built on the ATMEL ATMEGA series of microcontrollers, and depending on which version of the Uno you get, you will get different ATMEL chips, and they will vary in things like clock speed, the amount of RAM, the amount of flash memory, if any. Those are really the big things that drive, as you're just getting started, you'll have to, obviously also the number of I/O pins. So different classes within that family, different chips within that family will have different variants. So one thing you'll have to kind of figure out as you're designing, the first one really is number of pins. If you're doing a really complicated, say you're driving a bunch of LEDs, you probably will need a chip that has more I/O pins. If you're doing a project where size really matters, you may have to get a different, not just a different family of chips, but you have to get it in a different package type. So the Uno has it in what's called a DIP configuration, dual inline pin. So which basically means this chip right here, I could pull that out and replace it. And specifically on the things here, the Uno has the ATMEGA 328. Yeah, the 328P. And I just noticed that's upside down. There we go. So right here, at the end of the day, this really is the microcontroller chip, and this is what if you burnt something out, you could get online, go to Mouse or whoever, and buy this for probably like $1 or so. Everything else around it, kind of like your USB hub, your hosts, your little oscillator, some power filtering capacitors, LEDs, resistors, everything else is needed to make the ATMEL chip work, but really the microcontroller is that particular chip right there. So microcontrollers, what are they good for, and when should you use them? So microcontrollers basically are bare metal. In other words, you have access right to the hardware, and you write a single piece of code that runs in a continuous loop. You write that code, you upload it to your chip, and then that program runs in a constant loop. There is no operating system. There is no, so there's no overhead that you have to take into consideration. It's just your program running on the metal after it's been compiled and uploaded to your microcontroller. So what do you gain out of that? You gain speed, but because you're not writing an operating system, you have to handle more functionality yourself. You can't rely on an operating system layer to handle I/O functions or writing to a file or handling network. You have to do all that within the space and the memory that your particular microcontroller has. So again, that goes back to why you have to pick out different microcontrollers and look at things like memory size, processor speed, or clock speed, because you won't get the same performance using a lower end, though cheaper microcontroller. You may have to upgrade depending on what you're trying to accomplish, how complex your code is, how many, if you have different, in the case of Arduino, different shields. If you've got different shields and you're going to start adding like an Ethernet layer, everything you add to this, to the ATMEL chip has to handle, means it needs more resources to do. So microcontrollers are great because they're relatively inexpensive. There is, again, no overhead with an operating system. You are writing code that runs basically direct on the hardware itself. So, my opinion, they're a little bit easier to debug. You're not worrying about race conditions with some piece of software that you have no control over, that you don't know that's running. But you're kind of limited. At the end of the day, microcontrollers are really good for interfacing with sensors, with driving actuators, but they're really not good for doing process intensive of things. Like, I'm trying to say you wanted to have a webcam and you wanted to do something like motion detection. You're going to be pushing the hardware of most microcontrollers to do that with any sort of reliability or efficiency. There are different Arduinos out now, specifically one called the Yun. That's a hybrid solution between this and a single board computer that can do some more of that stuff. But before I get into that, let's kind of change gears and talk about things then, like, and I apologize because I have mine in a case. I should probably take the case off so you can actually see. So this is the Raspberry Pi, the first generation Raspberry B. I'm going to probably break the case. Okay, so I'll just leave the case on for right now, I guess. So, if you look at it, the untrained eye, you can tell there's some differences between the Arduino and the Pi. So one is there's integrated Ethernet. It has host ports for USB versus basically this is just this USB, is it the B type connector? You can't plug in a USB mouse and keyboard on the Uno. This is simply basically there to connect to your computer to have some sort of serial communication and to power the Uno. Whereas here I could plug in on the Pi a keyboard, a mouse, webcam, HDMI video out, composite video out, and then the audio out. So single board computer, specifically the Raspberry Pi, is really that. It is a computer. It is a full-blown computer, just in a very small form factor. And relatively speaking to your powerful desktop or laptop you could buy, it has limited resources. But at the end of the day, it's still a computer. It's running an operating system. In this case here, Raspbian, which is a distro of Linux. And though the Pi does have GPIO pins, or general purpose input output, like the Uno, the microcontroller, there's a level of indirection to access those pins, at least in the first generation. You're going to access these through software libraries versus kind of writing the code And again, sort of having more direct to the metal access that you would have on the Pi, or excuse me, the Uno. So advantages, disadvantages of a single board computer system. They tend to be processing wise more powerful, faster processor, more memory. You're running a full operating system, so you can link other people's software, so you can download webcam libraries or servo libraries that have already been written. And the other nice thing is, because it's again a computer, there's different languages. So you could do Python, you could do C or C++, whatever compiler you can get on to your particular distro. Whereas with the microcontroller, you're going to write whatever programming language, the IDE that's built or integrated development environment that is geared towards whatever microcontroller platform you're writing. So in the case of Arduinos, you are using a C-derived language called wiring. But with the Pi, you could, and I prefer the Python language, but you could do C, C++, Python. I'm sure there's probably some other ports of some other languages. But again, you have an operating system here that handles file I/O. It handles user input outputs for you, and then you, through your library files, handle those as just as you were writing a regular computer piece of software. Now, pros and cons. If you're trying to do something real time, you have to be running a real-time operating system. So, normal, and I think the Raspbian is not a real-time operating system. There's overhead. So while you think when you hit, sudo Python, whatever Python script you have, it's not always the thing that's running on the CPU. Just like your computer has overhead tasks to care and feed and manage that computer, a Raspberry Pi has to deal with interrupts to handle memory, to handle the accessing the SD card, which kind of acts as the hard drive for a Raspberry Pi. So your application, if you're trying to do something real time, may not actually act real time. Whereas with a microcontroller, again, though it's not perfect because you're running one main loop over and over again, at the end of the day, the only thing that is running on the microcontroller is your code. The Raspberry Pi, that's not the case. Again, if you're using a third-party library to handle, say, the webcam, that's running on top of your application, on top of the operating system. But it's a lot more powerful and more robust. They tend to have, again, faster CPUs, more memory. It's easier to access and have something like a hard drive, even though it's a SD card. And you have more programming language choices than a microcontroller. So single board computers, again, Raspberry Pi is very popular right now. Beagle Bone is another very popular and actually in some ways more powerful version. So, if you're writing an app on a Pi and you're finding that you're running out, you're not getting the performance that you need, there are other solutions. Look at Beagle Bone. Again, and this is kind of aimed towards, you're not necessarily a professional designer. You're not trying to you're not going to try to invent the iPhone killer with this type of hardware. But if you're just looking to kind of maybe be a small or medium business and do some custom hardware that you don't have to go out to big, cut multi-million-dollar deals with Chinese manufacturers, these type of solutions, you can make consumer grade products with this stuff. It's not like it's strictly an amateur kind of based technology. All right. And I apologize for the cough. It's a little dry here. So talk to about there's a third type, and that's called Field Programmable Gate Arrays, FPGAs. And like I said, they're not quite in the, there's not a lot of maker versions out right now. They're getting there. So this one here, I want to make sure I can get this so that you can actually see, is the Papillio, which I think is Italian or Greek or Latin for butterfly. And so when you look at it, right away you're like, well, okay, I see, there's my oscillator, there's one oscillator, there's my header pins, there's my header pins, this is the brains of it. This is the FPGA, just like, this really is the microcontroller. Well, this really is the FPGA. Everything else around it is just there to make it easier to use, power, cleaning up and doing my power, USB handling. So what really is an FPGA and what makes it different than a microcontroller specifically, but also, the single board computer. So when you program an Uno or any Arduino, you're actually writing software. You're writing a set of instructions that goes over and over in a loop, and their function calls and whatnot. But at the end of the day, you're writing software. An FPGA, you're programming in a language, and there's two popular ones. One called VHDL and another one called Verilog. And I think in the case of the Papillio, they're supporting VHDL. And VHDL in itself stands for VISC, Hardware Description Language. So the V is another acronym. HDL is Hardware Description Language. So the VISC part, VH, very high speed integrated circuit, VHSIC. So very high speed integrated circuit, hardware description language, VHDL, basically. So if you looked at it and you didn't know any better, you would think you're looking at some sort of maybe a C programming language. But what you're actually doing, you're not writing software in the sense, you're writing it in an IDE. It kind of has there's syntax. It looks kind of like, an object-oriented, maybe sort of programming like a C, C++. But what you're actually doing, instead of uploading that code, and it kind of, it treats it like a computer, and there's a program counter, and it just keeps walking around that your set of instructions. What you're doing with an FPGA is you're actually changing the hardware. You're actually inside here, you're configuring transistors in certain ways to actually basically create hardware. You are creating reconfigurable hardware. And it's kind of hard to get your head around at first. That, okay, I'm writing software, but what I'm really doing is basically telling this FPGA how to reconfigure its innards. There are blocks within an FPGA, and it's the same thing over and over again. Many of these blocks that you can tell, this block, I want you to be an inverter. I want you to be an AND gate. I want to be a certain type of flip-flop. And so what you get at the end is really fast products. So whereas, again, anything that's with software, there is some amount of overhead. In the case of the single board computer, third-party libraries, the operating system, the Uno and our microcontrollers is, you may have a button press, but if your code is not at the part where it's reading the button press, there's going to be a slight delay. Now you can get around with that with things called interrupts, and we'll talk about that maybe in a later episode. But at the end of the day, with an FPGA, because there's not software running in a loop, the hardware, all the hardware components you write are basically listening at all times. So if I had 5 buttons connected to 5 LEDs and I press them all 1, 2, 3, 4, 5, or 5, 4, 3, 2, 1, or some combination thereof, I would be able to detect that real time without having to sit there and wait in a loop. Because again, I'm not writing software. I'm telling the hardware how to configure itself. Now, again, it's complicated when you're first starting off to really explain that in a way that makes sense without getting into the details of what is an FPGA, how's it built. But suffice to say, if you need to do something that has that timing is critical, that you really want really real-time responses, eventually, and anything you can do in one of these, you can do in the other for the most part. So at the end of the day, say you're in the prototyping phase of building a product, you may start with a microcontroller. Eventually, you're going to start prototyping on an FPGA. And so this is like the big boys do it, right? The real professional grade. Because it's reprogrammable, I can tell that hardware how to reconfigure itself on the fly. But the nice thing is, because I'm writing it again, the standard language, VHDL or Verilog, when I'm done and I've tested the hardware out and I think I've gotten all the bugs worked out, that same file that programs the FPGA, I can then send off to a foundry and actually have that the output, again, the configuration, the inside of that chip, I can actually have now an application-specific integrated circuit, an ASIC, actually built specifically for my need. And then you're talking real fast, because now you've built hardware that only does the specific functions you want, and nothing else. And that's where you get the speed at. But FPGAs they're kind of like that happy medium between an ASIC and these other microcontroller or single board computer solutions, in a nutshell. Now, if someone's out there listening who is a PhD in double E or professional designer that's doing very high end electronics, there's a lot of nuances that I'm obviously probably skipping over and on purpose, and B, there's probably a lot that I'm skipping over because of my ignorance as well. My point is, I just wanted to point out that there is, when you look at chips and boards, don't assume all chips, all boards are built equally. There are differences. And again, even within one class, if you pick just microcontrollers, there's tons of differences within the microcontroller class. And then there's just differences, there's a whole horizontal layer of single board computer, microcontrollers, FPGAs. With that, there's a fourth type, actually, that even I don't know how to really explain what it is, but I know I like it, and I've been playing with these lately. And let me show one here. So this guy here, specifically this board here, and there's some other boards that come along for the ride. Let's see if I can get these up here without breaking anything. So, and I've talked about these in some other videos on the other podcasts. And again, I'm not sure how to quite explain what class of product they are, the class of on their own. In some ways, they're kind of the way when I first started in electrical engineering. It's exactly how I started. We used to have big old fat parallel ports, and we would actually, run resistors and LEDs right in the back of our computers, and there's some libraries that let you control the I/O ports of an old parallel port to make rudimentary computer controlled electronics. Well, This is like that done well professionally. They're called Fidgets. I haven't mentioned that already. And they're USB based. So you plug in little mini USB on one side, hook this into your computer on the other side. So you do need a computer, although it does work with a Raspberry Pi as well. So you don't need a multi-$100 computer. You can do this with a $25, $35 computer. And the best way to explain what a Fidget does is it takes they have these different little boards. Like this one here is a little rotation sensor, basically a potentiometer with a knob on it. This guy here controls a servo motor. But they all go through this little interface board, and basically it's a way for you to it reduces hardware to simply making software API calls. So instead of having to worry about configuring resistors or calculating what values you need for capacitors, you buy these little kits, you hook them right to LEDs, you hook them right to the servos, again, the potentiometers, and on your computer, you can download. They support a ton of programming languages. They support Mac, Linux, and Windows on the operating system side. And again, I prefer using the Python language. I can control the outputs, and I can read the inputs simply by making using their libraries and making basically function calls. So if I wanted to read what's the value of this potentiometer, it's simply a software call. I don't have to worry about understanding the underlying hardware. So it's a good way for if you've done your whole career, or you've started and you're a software person, but you want to start dabbling in electronics, the hardware side. Fidgets are a really cool way to get started to do some powerful stuff, because you can rely on, instead of having to learn the hardware, you can kind of build stuff relying solely on your software abilities, because it kind of makes the hardware just plug and play. Again, I don't know really, I don't know if this is considered, a class like FPGAs, microcontrollers, or single board computers, but again, this is kind of, to me, it reminds me of how I first started learning. But again, it's done in a much more professional and useful way. Let me switch back over here to this other camera. Boom, 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 boom. Okay, so that's kind of it for this episode. Again, I'm trying to get a feel of, I wanted to do a podcast where I did more tutorials, but trying to force it into the steam-powered podcast didn't feel the right way to do it. So Gears of Resistance is going to hopefully be that outlet for electronics, open and specifically open source hardware. So with that, I need feedback. Right now we're going to distribute this via the same steampoweredpodcast.com website, iTunes link. So it'll just come out instead of Steam Powered Podcast episode whatever, it'll be Years of Resistance episode whatever. So head over to the website, though. There is a link. It's probably going to be one or two stories down now, with a little Google Forms feedback sheet. And just tell me what you would like to see in a open source hardware podcast that is done with, again, the intent is to both be video and audio. Do you want to do interviews of projects? Do you want to do interviews of platforms? Do you want to do both? Do you want to focus just on projects? Do you want electronic tutorial hints and tips, like maybe one day we talk about voltage dividers, and the next day we talk about diode protection on a motor, and just little hints and tips and tricks? Or do you want to do like all the above and just keep changing it up? So that's the feedback I'm soliciting. Again, for right now, it's all on steampowerpodcast.com. And then if, depending on how this goes, we'll look to maybe stand up its own RSS feed and whatnot. But for now, that's all. So again, thanks for all the feedback we've received thus far. This is to give genesis to this podcast, and looking forward to hearing back from your feedback. And I guess with that, there's really nothing else I want to talk about. So until next time, please hammer us on the feedback, comments, leave it in the video, leave it on the website, Google Plus, wherever, and we'll try to incorporate as many good and creative and positive criticism as we can, knowing that we can't please everyone. But with that, I keep saying that's like the third time I've said that now, so I will shut up. Thanks for listening, and until next time, stay quirky.